In this video, we're going to work through several examples explaining why skeletal structures are the most common structural forms that you will see in organic chemistry, but they're related to many other forms of structures that you can see in different contexts, even though skeletal may be the most. So with that, we'll start with just defining all the different types of structures that there are, and then show why skeletal is usually preferred because it is the most abbreviated and the easiest to write. So let's first begin with Lewis structures. So Lewis structures explicitly show all of the electrons involved in a chemical bond to be explicitly Lewis. So here's an example of ethane, and it shows that we have this carbon atom is bound to another carbon atom through just 2 electrons, one from each carbon that is represented there. And then we have 3 single bonds to each of the hydrogens on each carbon, and again, we explicitly show the electrons from the hydrogen and the carbon forming that bond. Now this is explicitly Lewis, and you can see with all the dots that are necessary, it can be kind of cumbersome to write this, so this is why Lewis structures are usually not the most common way that organic chemists will illustrate their molecules. Okay, the next form is K-clay structures, and this might be the type of structure that you're more familiar with from just Lewis structures. The difference between Lewis and K-clay is that you show the electrons that are involved in a bond as a line. So what that means, what that looks like, if we go back to our ethane example, we have our carbon-carbon bond shown as a single solid line, which is representative of the 2 electrons, one involved from each carbon. And then again, the carbon-hydrogen bonds are shown as a solid line. So to be most accurate, this is a K-clay structure, even though it's very common that this is represented or called just a Lewis structure. They're related, but to be explicitly Lewis, you are showing the electrons not in a line, as in the case with the K-clay structures. But again, this is still rather cumbersome because you have to show all of these individual lines to each of the individual atoms, and we'll see that there are ways to abbreviate this. Okay, the next type of representation that we'll talk about is the condensed formula. The condensed formula is an intentional depiction of the molecular formula to provide as much structural information as possible. So this is related to the molecular formula, but it's different in the sense that the atoms are arranged in the condensed formula to kind of lead you to a Lewis structure or K-clay structure, or even a skeletal structure. So here's an example which explains this a little bit better, I think. So again, we're looking at ethane. So instead of looking, here's just a molecular formula, is C2H6, whereas the condensed formula is CH2 CH3. That's indicating to us that 3 of those hydrogens are bound at the first carbon, the other 3 hydrogens are bound at the second carbon, and then to fulfill the octet for both carbons, they must be bound to each other. The carbons must be bound to each other. If we have a molecular formula of C2H6, it would be possible for us to have isomers if we could arrange the atoms in a different way. With ethane, there's only one way to represent this, and it's with a CH3 bound to a CH3. But this is the point of the condensed formula, is that the molecular formula doesn't indicate what type of isomer you have. And in some molecules, in many molecules, the isomers are going to be present, and you'll need to be able to distinguish them. And this is where the condensed formula allows you to do that, again, without being as cumbersome as the Lewis structure or the K-clay structure. All right, the next representation to talk about is the skeletal structures, sometimes called the bond line formulas. I've seen both in different textbooks. So this is by far the most common. And the reason it's the most common is because there's a series of assumptions that are made that allow you to abbreviate the structure. So first, let's talk about the assumptions. So first of all, it assumes that all endpoints on your structure are carbons. So we'll look at an example and explain what I mean by that, but this is essentially where you're just drawing lines and they're not showing any atoms at all. So the assumption is at every endpoint of the line, there is a carbon atom that's there without you explicitly drawing a C. The second assumption is that if the endpoint, which as we just talked about is a carbon, that if an octet is not shown at that endpoint, then that octet is satisfied by carbon-hydrogen single bonds. So what I mean is if we see a carbon at an endpoint that's only bound to one other carbon, then there must be 3 carbon-hydrogen bonds at that carbon at that endpoint without explicitly drawing them. So this can be confusing, but we'll look at an example to illustrate this. So here we have butane. So again, what I was mentioning, the first assumption is that all of these endpoints are carbons. So I will number all the carbons in this molecule, which there are 4. So 1, 2, 3, and 4, because these are all of the endpoints. Now getting to the second assumption, which can be the more challenging one, is indicating how many hydrogens are at each of those endpoints. So if we look at carbon 1 or 4, they're both only bound to one other carbon. Carbon 1 is bound to carbon 2, carbon 4 is bound to carbon 3. So what that means is if there were no other bonds to that carbon, it would only have 2 electrons. And we know that it needs to have an octet. Carbons also don't like lone pairs, so we're not going to assume that there's a lone pair. What we do assume, since this is organic chemistry and organic molecules, we assume that there are carbon-hydrogen bonds to fulfill the octet, and they're all single bonds. So this hydrogen then, or this carbon rather, needs 3 carbon-hydrogen single bonds to fulfill its octet, because now if you count, there's a carbon bound to carbon number 3, and then the 3 carbon-hydrogen single bonds gives it the octet. Same with carbon number 1, there's 3 hydrogens necessary to give that an octet. Now if you look at carbons 2 and 3, they're both bound to 2 other carbons, namely carbon 1 and carbon 3 for carbon number 2. So it only needs 2 hydrogens to fulfill its octet. Now if you count, we have a carbon-carbon bond, that's 2, and then 2 carbon-hydrogen bonds to fulfill that octet. And then again, carbon 3 is more of the same. It is just like carbon 2. So this is why we draw these skeletal structures like this, because you can get all of this information from simply drawing this, right? These are equivalent structures. The only reason I marked up the first one so much is to explain what is all assumed and understood when you look at a structure like this, and it's the identity of all those, the presence rather, of all those hydrogens, carbon-hydrogen bonds that fulfill the octet for each of the carbons. Okay, so now we're going to look at butane as an example of each type of representation that we talked about. So first of all, we had our Lewis structure, and again, to be most accurate within the Lewis structure, you should represent each bond as the electrons that are coming from each atom, which is what's represented here. We have all of these pairs of electrons that form the bonds between the carbon and the carbon and hydrogens. So again, this is extremely taxing. It takes a while to draw this out. So the K-clay structures were invented to abbreviate this somewhat. So we'll look at the K-clay version next. So again, now here, it's still rather cumbersome because it's showing all the carbons explicitly with carbon-carbon single bonds, which is the line that is indicative of the 2 electrons in each of those lines. So again, there's a lot of atoms that you need to draw here. So this takes a while and is not the preferred representation. Next is condensed formula, and this is among the most common with the structural, or the skeletal rather, structure. So here the condensed formula shows that we have a CH3 group. Again, if we compare this to our K-clay or the Lewis, our CH3 is this kind of group. Then a CH2, again, that's this kind of group. CH2, again, that kind of group. And then another methyl group, the CH3. So the condensed formula shows all of this information without showing all those single bonds in the form of a line. And then to be the most abbreviated and the easiest to draw this is the skeletal structure, which is just simply the 4 endpoints, and then all of those hydrogens are understood, which gives you butane. So this is why the skeletal structure is used. It's because it's just the easiest and simplest to draw once you understand all of the assumptions that are made in that type of structure. Okay, for the remainder of the video, we are going to look at a series of examples that are asking us to represent the condensed formula into a skeletal structure. So again, this is the most common way to assess this because the condensed formulas are easy to draw and to give, and then the skeletal structures is the best way to represent it for something like a mechanism or any type of reaction. So you need to be able to interconvert between these types of structures very quickly and very easily, and that's the goal here. So let's jump right into it. So first of all, we need to count the number of carbons that we have total. Here we have a CH3, that is one carbon, CH, second carbon, and then two CH3s. So whenever you see this parentheses, it is telling you that whatever is in the parentheses is bound to the previous atom, the atom that precedes it. In this case, it's the CH. So here, without drawing anything, it's clear that this carbon is bound to this CH carbon. This carbon is then bound to one of these CH3s, and then it's bound to the second CH3. Since they're both in parentheses, because there's two of them, parentheses means it's bound to the preceding atom. So this is how that would be. So now let's draw it in our skeletal structure here. So we have 1, 2, 3 carbons, and then the fourth carbon is also bound at the 2 position. So 1, 2, 3. And let me draw it like this. 1, 2, 3. And then now that only shows one of the CH3s at the 2 position. So there's another CH3 at the 2 position, and this gives us the exact same structure. So now let's analyze this to see why this is the same. So here there's 3 hydrogens. Here there's 3 hydrogens. Carbon 1, there's 3 hydrogens. And carbon 2, there's 3 bonds already in the form of carbon-carbon bonds, so there's only 1 hydrogen. So now if we were to, again, convert this back to the condensed formula, carbon 1 is a CH3, which is bound to carbon 2, which is a CH. And then there's 2 methyl groups bound to the CH, which is carbon number 2, and that's why we put it in parentheses to represent that it's bound to that position. And there's 2 of them. So this confirms that it is in fact the correct skeletal structure from the condensed formula. This takes a lot of practice, so just bear with me and keep working through these and it'll begin to make sense. Okay, so jump right into the next one. So here again, we should identify the number of carbons. There are 3. There's this methyl group, carbon oxygen, and then a methyl group. So this can be kind of challenging because we need to identify what's going on with that carbon oxygen. So the first thing you can do is, just like I did in the previous example, count your carbons and start that as your chain. So 1, 2, 3, like this. Now, at carbon number 2, there is an oxygen that's bound there, right? So carbon 1, 2, and 3. 1 and 3 both just have the 3 hydrogens, so nothing going on there. But we do have an oxygen at carbon number 2. So if we were going to draw a single bond to an oxygen, now let's consider the number of bonds to carbon number 2. Well, there's 1 to the oxygen, 1 to this carbon at 1, 1 to the carbon at 3. So that's only 3 bonds, so it would not have an octet. So we would need to have a hydrogen bound to that carbon number 2. And we look at our condensed formula, there is no hydrogen near carbon 2 because these 3 hydrogens are with carbon 1, these 3 hydrogens are with carbon 3, and that's all that there is. So there cannot be a hydrogen at carbon 2. And if we think differently and we look at the oxygen, for the oxygen to have an octet, it would have to have 3 sets of lone pairs, which would indicate that it would have a formal charge of -1. So then the carbon number 2 would have to have a positive charge, and this would be far too unstable. There's a better way to look at this. So instead of trying to add lone pairs and charges to stabilize this and fulfill the octet, the other option is to put a carbon-carbon double bond. Now, if we look at carbon number 2, that carbon now has 4 bonds because it has this carbon-carbon double bond, which is the two bonds, and then 1 to carbon 1, 1 to carbon 3, that's 4 total bonds. So that carbon now has an octet, And there's two lone pairs on the oxygen. Now, formal charge-wise, this is all neutral, and this is consistent with the condensed formula. Again, if you just look, carbon 1 is a CH3, then carbon 2 is just a quaternary carbon that's bound to the oxygen, and then a CH3. Okay, which is matches our condensed formula. All right, hopefully this is making sense. Move on to the next question. Okay, here once again we should look at what's our longest chain going on here. So this oxygen is different than the previous one because the carbon that precedes it and that is after it both have hydrogens bound there. So that means that the oxygen is essentially a part of the chain. Okay, so let's look at that. So we have a methyl group, then the oxygen that's part of the chain, then a CH2 group, and a chlorine. Okay, this is going to be our structure because now if we look at it, we have a methyl group here, or all the hydrogens on this methyl group, I should say. This is carbon number 1. And then 2 is our oxygen, which has 2 lone pairs to give it no charge. And then position number 3 now, our second carbon, has 2 hydrogens to fulfill its octet. Carbon 4 has 2 hydrogens rather. And the chlorine then has 3 sets of lone pairs to give it a net neutral formal charge. Because chlorine is a halogen, so it wants a valence of 7 to be neutral. We have the 6 in the lone pairs and then the 1 bond, so 7 minus 7 is 0. So this is the correct structure. If you were to incorrectly think that carbon 1 was bound to carbon 3, so something like this, right? So here we still have our 3 carbons, so 1, 2, and 3, and then our chlorine and the oxygen. So the issue with this is that the 2 position would be a CH, and we don't see any CHs in our condensed formula. And the oxygen, again, assuming it has an octet, would have a negative charge, which is an issue because we're going to assume that all of these compounds are not charged if there's no charge indicated in the condensed formula. So hopefully that makes sense why this is incorrect, and this is the only possible way to represent it consistent with the molecular formula, is this first option. Okay, move on to the next one. So here we have an OH and then a CHO. So this is very important to know the difference between these two. So again, here it's useful to start with just identifying our chain of carbons. So it's these 4 here. So 1, 2, 3, and 4. And then at carbon number 1, we have an OH. Right, like this. And then at carbon number 4, we have an oxygen, but it's an HO. So again, let's just put a single bond to our oxygen and we'll revisit that. Let's start with the left side. So if we look at the left side of carbon number 1, this carbon number 1 would have 2 hydrogens because the single bond to the oxygen, the single bond to the other carbon, carbon number 2, would give it its octet. So this is consistent with what we have there in our condensed formula. Carbon 2 would have 2 hydrogens as well because it's bound to carbon 1 and 3, and then carbon 3 would have 2 hydrogens as well. Okay, so now this oxygen would have 2 lone pairs, again, to give it a formal charge of 0, and it's bound to that hydrogen, which is consistent with an OH. Now, if we look at carbon 4, this is the real problem. So we see that carbon 4 is only has 1 hydrogen on it because it's CHO. If it was COH, we would say that that oxygen is bound to the hydrogen. But since it's CHO, we're saying that the carbon is bound to the hydrogen, not the oxygen. So This means that if, just like in the previous examples, if that oxygen is not going to have a negative charge, which we're going to assume there's no charge if it's not mentioned in the condensed formula, it must be a double bond, which is in fact the correct answer for this one. Carbon number 4 is a carbonyl in the form of an aldehyde, where it's double bound to the oxygen, and then it has a hydrogen, an R group, and then a hydrogen at that center. Okay, so that is the takeaway from this question, is that a CHO is an aldehyde in the condensed formula representations. Okay, and here's our last one of this set. So again, identify your longest the chain of carbons here. So 1, 2, and 3. There's 2 other methyl groups, but they're going to be bound at carbon number 2, again, because of the parentheses indicating that. So 1, 2, 3 is how we can start. Let me use a different color here. 1, 2, 3. Okay, so 3 is a part of one of the methyl groups in the parentheses. So then 2 more methyl groups are bound at carbon number 2. So we draw that like this to be consistent with Vesper bond angles. So this is now the correct structure, because we have a CH3 bound to carbon 2, a CH3 bound to carbon 2, and a CH3 bound to carbon 2. That is this, that is this group that's in parentheses. And then carbon number 1 is another CH3 bound to carbon number 2. So this is essentially a T-butyl group bound to a methyl. All right, here is another example. And this one is pretty confusing because we have a CH2, and there's 2 of them bound to an oxygen. So if we think about this, let's just think if we had a CH3, oxygen, CH3, that's kind of similar to this, except for the fact that this is CH2 and there's 2 CH2s. So this wouldn't work because this would be CH3O CH3 would be the condensed formula, or I suppose you could write this as CH3 2O to look somewhat similar to what we have in our actual question. So the issue becomes we need to get rid of a hydrogen at both of the CH3s. So the only way to do that, since we already have bonds to the oxygen, is that we need to add a carbon-carbon bond. So what the answer actually is a epoxide, which is a 3-membered ring in which the carbons are bound together. So now if we look at our structures here, this is 1 and 2. Carbon 1 is a CH2 group. Carbon 2 is a CH2 group. So this gives us the correct formula now, because we have a CH2, there's 2 of them bound to the oxygen, so this is the correct answer. So you kind of have to play around with this one. It's very difficult to represent rings in condensed formulas, so that takes a little bit of extra practice. Okay, let's look at the next example, number 7 here. So we have a CH2 and then double bound to this carbon. That's what this equal sign looks like. So it's a carbon double bound to this carbon. Then this carbon is bound to a chlorine and to this methyl group. Right, so our chain of carbons is 1, 2, 3. So 1 is a double bond, 2 is here, and then we have a methyl group. That's 3. Right, so 1, 2, 3. And then there is a chlorine at carbon number 2 as well. That is here. And then, of course, we have lone pairs at the chlorine to give it no charge. And then there's those 2 hydrogens at carbon number 1. Now you may be wondering, is this going to be cis or trans? The answer is no, there's not going to be any cis or trans because we have 2 hydrogens at one side, so you could not pick priority of either of those hydrogens, and that is that's why it would be not cis or trans. It's just achiral. There's no geometric isomers. Okay, moving on. Here, again, let's start by identifying our chain of carbons. So we have carbon 1 here. This methyl group is bound to carbon 1, so that's not part of the chain. This is part of the chain now. This carbon is bound to this one here. This is part of the chain as well, and then this terminates it. So one of the methyl groups terminates the chain. So the simplest way to start this is just draw what looks like butane, 4-carbon chain, like this. And now it's a matter of putting everything else on this chain. So carbon 1, 2, 3, and 4. So at carbon 1, there's a bromine, right? That's here. So let's put the bromine at that position, carbon number 1. And then at carbon number 1, there's also a methyl group. So that is the CH3 there. That's what's in parentheses. So I've marked both of those at carbon number 1. And then at carbon number 2, there's just 2 hydrogens, so there's nothing there. And then at carbon 3, there's 2 methyl groups. So right now we've only drawn 1, so the second one is at carbon 3. So I'll redraw this since my numbering kind of messed it up. All right, so this is the same structure that I just drew, 2, 3, and 4. So again, carbon 3 is bound to a methyl group, and then another methyl group, which is carbon 4. Carbon 2 is just bound to the 2 hydrogens, so nothing there. Carbon 1 is bound to the bromine, and then to this methyl group that's in parentheses. And then again, the bromine has 3 lone pairs, just like the chlorine, to give it no formal charge. Okay, moving on to the next one. So here, again, our longest chain is 1, 2, 3, 4 carbons. So again, a butane-like structure. And then, so carbon 2, so 1, 2, 3, and 4. So carbon 2 has that CO again. So, and there's no hydrogens there. So that has to be a carbonyl, has to be a double bond to the oxygen, like we discussed before. So look at the previous questions if that is it making sense. I think it was question number 2 that explains this more thoroughly. So that is now position 1, 2, and 3 is like this. So now position 3 is bound to 3 methyl groups. We're only showing 1 so far. So there's 2 more methyl groups drawn like that, and that gives us the structure. More common way to represent this is to draw your T-butyl group like that, where this is no different than what I drew. Both are completely acceptable. Here's carbon 3, which then now the methyl groups, instead of being like down and to the right here, they're like up and down, but it doesn't make any difference. So by the way, this is 4, not a hydrogen. Just want to be clear about that. This is carbon 4. It's the same as that methyl group. Okay. Now let's do the last one. Here we have again, let's identify our longest chain. So a methyl group first, CH, a CO, which is a carbonyl, then carbon 4, 5 bound to the chlorine. So 5, we'll draw a pentane to start. 1, 2, 3, 4, 5, like so. Carbon number 1, so let me label this 1, 2, 3, 4, and 5. So carbon number 1 is a part of this isopropyl group at 2. So 2 is bound to a CH3 and a second CH3. Right, so now this CH3 at 1 is one of these in the parentheses. The CH3 at 2, this one going up, is the other one. So this group and this group are the parentheses. Then there's a hydrogen at carbon 2, the CH, and then 3 is a carbonyl. So this has a double bond. Again, my numbering gets in the way, but I will redraw it. So, but that's carbon 3. Carbon 4 is a CH2, so that's good as is. Carbon 5 is a CH2 bound to a chlorine. So we add a chlorine at carbon 5, and again, it has its lone pairs to give it no charge. no formal charge. Okay, now let me redraw this so it looks a little bit cleaner. Okay, and then here we have carbon 1, 2, 3, 4, 5. And the lone pairs on the chlorine, of course. All right, so that is all I have for this video. I hope you enjoyed it and learned something. If you did, please leave a like and subscribe to the channel for more content like this. If you have any questions, feel free to leave them in the comment section below and I will get to them as soon as I can. If you have any topic suggestions or anything that you think that I can improve the video quality with, please let me know in the comment section below as well, and I'll be happily take your suggestions. So with that, I hope you all have a great day, and I'll see you in the next video.